In this video, we're going to talk about the area between curves. So we recall that our definite integral is defined as a limit of a Riemann sum. So we look at the limit as n goes to infinity of the summation of a function of this x sub I star. So the x sub I star again is a sample point in the ith subinterval multiplied by delta x, or the width of that subinterval. So remember that your first interpretation of definite integral was area between a y equals f of x and the x-axis on an interval from a to b. So a good chunk of this time spent in Calculus 2 is extending this exact same notion to other applications. So in this case, we're going to not just look at the area between a function and the x-axis, but we're going to look at the area between two functions. So let's say we have y equals f of x and y equals g of x defined on the interval from a to b, where our f of x is greater than or equal to our g of x for all x in the interval from a to b. Remember when you did area between a function and the x-axis, your first hypothesis that you made was that the function values were all positive. The graph of the function lied above the x-axis, but you could also handle it if the function dipped below the x-axis. So here, same idea. We're going to first assume that we've got an f of x lying above g of x the entire time, and then we'll talk about what happens if they end up switching relative positions. All right, so here's the setup for this. So we would have our function, f of x would be this red one here, lying above the function g of x, which would be the blue one here, on the interval from a to b. This would be the setup, and we are looking for that purplish shaded region, the area of that purplish shaded region. All right, so we'll proceed like we did when we were finding area under a curve. We're going to divide our interval up into n subintervals of equal width. So remember, we refer to this as a partition of the interval from a to b. So we'll use x naught to represent a, x sub n to represent b, and split it up into pieces using refer to the endpoints of each of those intervals. So the x sub I minus 1 comma x sub I is our ith subinterval. We're going to choose a sample point, our x sub I star, in that subinterval. Again, this is just like what we did for finding area under a curve before. All right, so again, here's the setup. I've shown just one rectangle. Of course, we would have several that would be going along here. So again, our x sub I star here is representing the sample point here for our ith subinterval. I haven't illustrated the ith subinterval, but those would be our left and right sides, the x-coordinates of the left and right sides of this rectangle. So our x sub I star is somewhere in the middle. The x sub I star is what we're going to use to help us calculate the height of that rectangle. The width is easy. The width is always going to be our delta x. We chop up our subinterval into those pieces. The delta x is the width of that subinterval. That's going to be the easy dimension for our rectangle. But we have to use our x sub I star to help us get the height. So we notice that the top of the rectangle hits our function f of x, the higher one, and then the bottom of the rectangle hits our g of x, the lower one. So we can calculate the height of that rectangle by simply doing f of x sub I star minus g of x sub I star. That'll be the height of a rectangle, and like I mentioned before, the width of the rectangle is going to be delta x. So we can find the area of the rectangle just by multiplying those two quantities together, height times width. Adding all of those areas up gives us this summation, sum from I equals 1 to n, height times width, so area of each of those rectangles. What we notice here is that this piece is a function of a sample point. I can write it, if I wanted to be fancy, I could write it as f minus g of x sub I star. So this is a function of a sample point times delta x. That's exactly the form for a Riemann sum. So when we take the limit of a Riemann sum, we get a definite integral. So our area then is defined as the limit of this Riemann sum, which again, like I said, is going to be equal to that definite integral. So now we can calculate the area between the two curves using the fact that we've got a definite integral here, and we can use the fundamental theorem of calculus, assuming that we can, of course, find an antiderivative. So let's see if we can do an example of that. So let's say we want to find the area of the region enclosed by the function y equals sine of x and y equals x, and then the interval that we're interested in is x equals pi, the pi over 2 to pi. So that's what the x equals pi over 2 and the x equals pi is giving us. So here is a picture of the region. Here is y equals x. Here's y equals sine x. Pi over 2 to pi. So we're looking at this shaded region here. On the interval from pi over 2 to pi, we see that y equals x is above y equals sine x the entire time. So the x is the bigger function, the sine of x is the smaller function, so to find the area, we'll do the integral from pi over 2 to pi of x minus sine x dx. Rather than trying to go through a limit of a Riemann sum, which would be really, really difficult here with the sine function being in there, to calculate the area, we're going to now be able to use the fundamental theorem of calculus. So find an antiderivative. An antiderivative for x is 1/2 x squared. Antiderivative for minus sine x is a plus cosine x. And since I've got a subtraction here, I could do that piece by piece. We'll plug in our endpoints then. Plug in pi. Cosine of pi is -1. That's where that -1 is coming from. Put in pi over 2. Cosine of pi over 2 is 0. That's where that 0 is coming from. And if you simplify, you get 3 pi squared over 8 minus 1. So that tells you what the exact value of the area is of that region on the previous slide. We can do these exact same techniques when we have boundaries that are functions of y rather than functions of x. So let's do that as an example here. Let's say we want to find the area of the region enclosed by x equals y squared minus 2, x equals e to the y, and then the interval that we're going to be interested in for the y's is going to be -1 to 1. That's what these last two boundaries are telling us. Look at a graph here. The x equals y squared minus 2 is the sideways parabola. X equals e to the y is really, if you think about just reversing, that's y equals log of x, natural log of x. So that's what that function is. Y equals -1, y equals 1. So we get this region. Notice that we would not want to integrate this with respect to x. Okay? And here's why. If I integrate with respect to x, then I need functions of x. So the first thing I would need to do is convert all these to functions of x. But notice that this would be a complicated problem to figure out the area based on the region. Notice that when I slice up my x-axis, my rectangles would go vertically this way. So notice from here, from -2 to 1, we would hit the parabola on both sides, the top portion of the parabola and the bottom portion of the parabola. Once we get from -1 to, this is 1 over e here, once we get from -1 to 1 over e, we would be on this rectangular region here. And then when we go from 1 over e to wherever this is, which is going to end up being e actually, we would have a top curve of y equals 1, but then a bottom curve of y equals log x. So you would have 1, 2, 3 separate area calculations that you would have to do to get that area. So looking at the way this region is formed, I would not want to integrate it with respect to x if I were able to. Okay, so we look at this, instead of integrating with respect to y, slicing it horizontally rather than vertically. Notice we get the same right bounding curve, same left bounding curve for the entire region. So I can set up one integral to do this. So just restated here, the graph of x equals e to the y is to the right of the graph of x equals y squared minus 2 over the entire interval. So I can do quote unquote top minus bottom. In this case, it's right minus left. Okay. So when we integrate this, then we will do top minus bottom relative to y. So again, right minus left, the exact same way we did with functions of x. So our area then will be the integral from -1 to 1. E to the y is the bigger curve. Y squared minus 2 is the smaller curve, dy. And again, now that we've got this set up, we can use our fundamental theorem of calculus. Antiderivative of e to the y is itself. Antiderivative for y squared is 1/3 y cubed. Antiderivative of 2 is 2y. And notice you get a minus, which just changes that to a plus. Plug in our values and get e minus e to the -1 and then plus 10/3. So again, notice we did this in the exact same fashion that we did for functions of x. This just was an easier way to do this with the way that the functions were given to us in terms of y. All right, so what happens if we have a top or a right boundary that changes at some point in the interval? So typically when that happens, we'll have 2 or more integrals that we'll have to use to compute the area. So let's look at an example of that. Let's look at the region enclosed by y equals cosine x, y equals sine 2x, on the interval from 0 to pi over 2. We notice here, here's x equal to 0, here's x equal to pi over 2. It's actually where these two curves cross. From here to here, the cosine curve is above the sine curve. But from here on over, the sine curve is above the cosine curve. So we don't want to do cosine minus sine the entire interval, because then we would be calculating this area as a negative area. And likewise, I wouldn't want to do sine minus cosine, because then this left one would be calculated as a negative area. So when we do this, we're going to split it at this where they intersect. Okay, we're going to write an integral to calculate this area, an integral to calculate this area, and then add the two pieces together. So again, since we see that we have that where they intersect, that's telling us that the top boundary curve switches at that x value. So let's see if we can find it. Set the two curves equal to each other. We know an identity for sine of 2x. That's 2 sine x cosine x. So rewrite that as an identity and put everything on one side so that we can factor out a cosine. And then set each piece equal to 0. We get cosine of x as 0, or solving for sine of x, we get sine x as a half. Now, of course, we know from our study of solving trig equations, these two would have infinitely many solutions. However, we really only want the solutions that are in the interval from 0 to pi over 2. So this first one is going to give you a solution of x equals pi over 2, which we saw that was the right-hand endpoint. It's also where those two graphs came together at that right-hand endpoint. The one we're really interested in is where the sine is equal to 1/2 in this interval, and that happens at pi over 6. So it's that second one is where we're going to look at splitting our, if you will, our integral into two pieces. One will go from 0 to pi over 6, and the other will go from pi over 6 to pi over 2. So we can now write the area as those two separate ones. So on the interval from 0 to pi over 6, the cosine curve is above the sine curve, so we do cosine x minus sine 2x on that interval. Vice versa, on pi over 6 to pi over 2, the sine curve is above the cosine curve, so we'll do sine 2x minus cosine x on that one. Again, use our fundamental theorem of calculus, get our antiderivatives. Here, with the sine 2x, you would have to have a 1/2 out in front to adjust for that too. If you need to do a u substitution, you can do it that way, but again, think about when you would differentiate, that 2 would pop out using the chain rule. So I need that 1/2 out in front to get those to cancel. So that's where the 1/2 is coming from. Plug in your values here, and it simplifies to 1/2. So this gives you an introduction into finding area between two curves, which we will discuss more in class.